Hello and welcome back to Fourier Transform, the video series where we talk a lot about the so-called Fourier series. And indeed, in today's part 7, I want to show you the complex version of this series. And it turns out it's not more complicated, it's the opposite. It's much easier to write down the formulas for the complex version. However, as always, before we start with the definitions, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via Patreon. And please don't forget, as a supporter, you get additional material with the link in the description. For example, you can download printable PDF versions you can use for learning this subject. So then let's start with what we already know, namely that we consider two pi periodic functions. And we also want that they are square integrable, so we write f is in L2. And you know, we consider this special case because there we have an inner product, which implies that we can simply calculate orthogonal projections. Hence, for every natural number n, we get a trigonometric polynomial called fnf. And then if we go through all natural numbers n, what we get is the so-called Fourier series. And now what we did in the last video is to describe this trigonometric polynomial with cosine and sine functions. However, we already know that we can substitute these functions with exponential functions. And in fact, this is completely equivalent because we work in the complex numbers nevertheless. Hence, by going to the exponential functions here, we don't lose anything, we just gain simplicity. Therefore, in this video, we will just explain how we can go to the exponential functions and how the formulas look like. And as you might already know, the essential ingredient here is just Euler's formula, which simply tells us that the cosine of x can be written as 1/2 times e to the power ix plus e to the power minus ix. Okay, so this is what Euler's formula tells us for the cosine function, but we also have a nice formula for the sine function. Namely, there we have 1/2i times e to the power ix minus e to the power minus ix. So you see, very similar, just with the minus sign here and the factor 1/i there. And indeed, this is already all we need to transform our trigonometric polynomial. And in order to see this, let's look at an example. So let's say we have a linear combination of cosine and sine functions. So for example, a times the cosine function plus b times the cosine function with the 2 inside. And then also plus c times a sine function. And this should also be the sine function with the 2 inside. Now, in general, we could say that these coefficients are complex numbers. Still, the input x is a real number, but the output of the trigonometric polynomial could be a complex number. So you see, this is not a big difference to the real case, we just also allow for complex coefficients. However, now we can just put in what we know from Euler's formula from before. So the first thing we get here is a/2 times these exponential functions. And then, of course, we can do the same with the second term in the sum, which is b/2 times the exponential functions, but here we have i2x in the exponent. This is important to remember because we have the same now with the sine function. The only difference is that we have I in the denominator here and the minus sign there. But now you should recognize that we find the same exponential functions at different positions in our term here, which simply means that we should put these together. So let's simply rewrite it as an ordinary linear combination for the exponential functions. In other words, we just have to put the correct coefficients together. So for example, we have b/2 plus c/2i. And this is the coefficient for the function e to the power i2x. And the function with the minus in the exponent, we also find the coefficient with the minus sign here. Okay, so there we have it. This is a linear combination of 4 exponential functions where the coefficients are given by complex numbers. And now what you should see is that we actually put in 4 cosine and sine functions as well. It's just that the coefficient for the function sine of x is given as 0. Hence the term in front of e to the power ix looks the same as this, it's just that the second part here is 0. Hence what you should remember here is that we have an equality, so we can go from the left to the right hand side and the other way around. Therefore, for complex linear combinations, there is no difference at all between the trigonometric functions given by cosine and sine functions and the exponential functions. And with that, we have the important fact of this video, something you definitely should remember. Namely, in our space of the trigonometric polynomials that are complex valued, we have two possibilities to describe subspaces. For example, we can take the span of the vectors that are given as the constant function, then the cosine functions until cosine of nx, and then the sine functions until sine of nx. Hence we see we have 2n plus 1 functions inside this span. And now, as we have learned before, this span can also be written with exponential functions. And there let's start with the one with the minus sign, so we have e to the power inx. And then we just reduce this factor n to n minus 1 and so on until we reach 1. Then we already have n functions, and then comes the constant function. However, now the nice thing is that the constant function we could also write as an exponential function, namely as 0 times x. So this is always 1 no matter what x is, hence we have the constant function x to 1. And then we just continue now with the plus sign in the exponent. Therefore, maybe also for 0 we already write a plus sign. Okay, there we have it. We increase everything until we have e to the power inx. And now you will believe me that we can do the same calculation as before for this general case to see that both spans are exactly the same. In addition, we can say even more, namely how the coefficients transform. So on the left here we have the coefficients as we have it in the first span, and on the right we write it for the second span. And there it's much easier because we only need to write one sum. However, there k should go from minus n to n. There it's important to note that we also have exactly 2n plus 1 terms. And now the coefficients we use for the exponential functions are usually called ck. And now what we have is that this k is in the power of the exponential function. And there you should see, with the sum, we actually go through all the exponential functions here. Okay, and now we can go through the calculation from before again to say how the coefficients ck are given. And there you might remember that we have to consider at least two different cases. So let's start with the case that k is greater than 0. Now, if you recall what we have done before, you will see that we have to combine cosine and sine functions together. So we had 1/2 coefficient of the cosine, which is ak, plus 1/2 coefficient of the sine function, so bk, but also with the factor I. And indeed, it's the coefficient bk over I. Okay, so with the factor 1/2, this is exactly what comes out of Euler's formula for the case k is greater than 0. And in addition, for the case k is less than 0, we had a similar thing, just with a minus sign. However, we cannot simply write it as this, because a negative k for the coefficient ak and bk is not defined at all. So what we actually have is the corresponding positive k, so what we can write is minus k for the index here. Of course, from before you know it's exactly the same coefficient, but we have to make the index fit. Okay, then only one case remains, namely what is about the constant function. Of course, for the constant function we don't need Euler's formula, which means the coefficient is exactly the same. Hence, C0 is exactly the same as here on the left hand side, which we write as A0 tilde times 1 over the square root of 2. And there please recall that we had to choose this constant function as 1 over the square root of 2 because we wanted to have an orthonormal basis here. And now it turns out that for the representation with exponential functions, we don't have to do such a strange thing like there. Therefore, also writing down an O and B with the exponential functions is much simpler than with the sine and cosine functions. So this is exactly what we will do now, and let's fix it as a result of this video. So as we have done it before, let's take our 2π periodic functions that are square integrable. And then after some steps, we reach our L2 space, which has an inner product. And then the trigonometric polynomials lie inside this space as a subspace. And please never forget, the inner product we consider here is given as an integral. So if you take two functions f and g and put them into the inner product, then we have f and g inside the integral as a product. The only thing that is important if you consider complex numbers is to add a complex conjugation for f here. And now you might remember that we tried different constants in front of the integral in order to get out the best O and B. And now it turns out that the factor 1 over 2π is perfect for our exponential functions. So you see, what we want to do is to divide by the period length. However, you already know this factor is not important for the orthogonality, it's just to normalize the vectors in our O and B. Hence, you should recall part 4 that these functions we call Bn form an O and S in our inner product space. We say O and S for an orthonormal system, which means each vector here is normalized with respect to the inner product and two vectors are orthogonal to each other. And since we have chosen the factor 1 over 2π here, we need the square roots of 2 in front of the cosine and sine functions for the normalization. However, in this case, the constant function is just the constant 1. However, now we also have a second O and S, and let's call it En. And this is much simpler to write down, because all the exponential functions look the same. So we can just write e to the power I kx, where k goes from -n to n. So it's really easy to write down. And this is the advantage, because we have two O and S, but we already know they both span the same subspace. But the notation for the second O and S here is just much shorter. And we can make it even simpler by just calling the vectors inside ek. Now, we didn't show exactly that we have an O and S here, but it's not hard at all. So it's not hard to show that two different exponential functions are orthogonal and that they are normalized. I tell you it's not hard because integrating exponential functions is not a problem at all for us. But still, it's something you should write down for yourself. Okay, now since Bn and En span the same subspace, we know that the orthogonal projection is exactly the same. And we already know the Fourier series is given by an orthogonal projection. Which means now we also have a much simpler representation of this Fourier series. Namely, we simply have a sum over k, where k goes from -n to n. And then we just have the O and S, ek, first as a vector, and then in the inner product. So this is just the standard formula of the orthogonal projection of f onto this subspace. And you already know the coefficients here given as inner products are called Fourier coefficients. And since here we don't have to distinguish cosine and sine functions, we only have one formula for the coefficients. So we get two things you should remember here. First, the Fourier series of f is given as a linear combination of exponential functions. And there you know the coefficients we simply call ck, and they are given by a nice integral formula. Simply because we know ck is given as this inner product, so given as an integral. First we have our factor of the integral, 1 over 2π. Then we have the integral from -π to π. And then we have ek here on the left, which means we add a complex conjugation to it. So it's important to remember, here inside the integral, we have a minus in the exponent. And then we just have f of x dx. So this is the formula, easy to remember, and it holds for every k between -n and n. In particular, it also holds for k is equal to 0, where we have the constant function 1 here. So we don't have to distinguish and remember different cases here, but the result is exactly the same. It's the Fourier series of f. So even if f is a real valued function, we represent the Fourier series as a complex linear combination here. Of course, in this case, the result would be that the whole sum here gives us a complex number with imaginary part 0. So this is the whole idea. Working with the complex version is much easier, but we don't lose any information. Maybe you could say we lose some visualization because we don't have the cosine and sine functions as graphs anymore. But still, what we get here is a whole sequence of trigonometric polynomials, and we call it the Fourier series of f. And if you want to distinguish it from the real version of the Fourier series, you would say this one is the one with complex coefficients. Or more precisely, it's the one where we use exponential functions. And now, since everything is much simpler with the exponential functions, we will continue with these. Therefore, I would say let's meet in the next video where we continue talking about this approximation of functions with Fourier series. So have a nice day and bye bye.